I'm Dave. Welcome to my shop. Today in Dave's garage, the Tiki Fire Umbrella project continues. They say a journey of 1,000 miles starts with a single step. Today we'll actually take our first 4 steps towards RGB LED glory by building something tangible and flashing code onto it that makes it do something cool. Join me as we use the ChipCam and Visual Studio Code to make a $2 chip on a $7 board sing and dance with the Arduino SDK. If you're okay with a little software and electronics, then strap on in because we're starting right now. It'll be small, but it'll have colorful LEDs and it'll be powered by an ESP32, and that's what really matters. Microcontroller control of a visual display that color cycles LEDs. If we're going to light the candle on the Tiki Fire Umbrella project, we obviously need to be able to control LEDs digitally. Speaking of which, these might seem like baby steps, but I assure you they form the essential elements of any microcontroller project, so that's where we're going to start to roll this snowball. Turning on an LED, then getting it to blink, then dimming it, and then making a color cycle through the entire rainbow. We're going to do all of that on this little circuit board from a website called EasySBC.com. They are but one of dozens of companies that make little tiny boards about the size of an old CPU that contain a microcontroller and a serial port and everything you need to communicate with the chip on board. They will all generally contain the same basic ESP32 chip, but each vendor uses their own recipe for power supply and serial port and so on. There are 2 big decisions I have to defend here: the selection of the ESP32 as our microcontroller and of the EasySBC board for our first couple of experiments. We'll be staying with the ESP32 long term, but after today we're going to migrate to a different development board, one that adds a tiny TFT video screen right on the chip for easier debugging. Anyone who is surprised with my selection of the ESP32 likely assumed we would be using the Atmel series of chips, which is what the Arduino SDK was created for in the first place. It was only adapted to the ESP32 later. But I'll boil it all down to a very simple fact. The ESP32 is just orders of magnitude more powerful and capable and costs about the same as an Atmel. We're talking about $2 in any quantity, so if you still have concerns about cost, you must be talking about volumes that are way above my pay grade. What specifically does the ESP32 add? Well, for comparison, the AT-Tiny chip in the Atmel series has 512 bytes of RAM. The VIC-20 had 8 times that 40 years ago. The ESP32 has 512K of RAM, 1,000 times more, and more important, a practical amount that you can actually accomplish things in. Rather than a single core at a pedestrian at 8 or 16 MHz, it has dual cores that are blazing 240 MHz each. And again, same ballpark cost. The ESP32 also has onboard Ethernet, Wi-Fi, Bluetooth, infrared control, DACs, ADCs, PWM generators, and more acronyms than any project really needs to be successful. Suffice to say, we'll start out blinking an LED, and we'll wind up with a chip that can do full motion video at the same time as it analyzes and reacts to the room music, runs a jQuery web server, and responds to a phone app. I think you'll be more than impressed with what is possible. There are a number of reasons I like this particular board. For starters, it's under $10, it's reliably available, and it has been for quite some time. From a practical standpoint, it's narrow enough to fit on a breadboard and still have its pins numbered. But the real reason for using it for our first adventure is that it has tricolor LEDs right on board, so we don't need to put it in a breadboard, or solder anything, or connect any jumpers or wires. In fact, if you'd like to follow along with me as I demonstrate, I will now complete the hardware portion of today's episode.
Careful.
Almost got it backwards. There we go. Check the video description for a list of the relevant software, as well as a link to where you can purchase these boards and the ones for upcoming episodes. Well, as the late great Leif P once said to me in a job interview, it's time to stop talking and write some damn code. So let's go do it. For today's adventure, we'll be using an ESP32 mounted on a board from EasySBC.com. What I like about this board is it's really simple, it is easy to program, and it has 2 LEDs. So they're built in and they're both tricolor. That allows us to do some experimentation with no breadboard, nothing else, just plug it into power like you saw at the very beginning. That's how we're going to run it. Let me give you a quick little tour of the board. The ESP32 itself is located up in this can here. Here you have the 2 LEDs, the left one being connected to the serial port and the right one being connected to pin 16, 17, and 18 of the ESP32. In the middle here we have a low dropout regulator, I believe, and below that we have a UART, which is used for programming the chip and communicating for serial, so it does not tie up one of the 3 onboard UARTs. But they chose to use one of some description here to avoid wasting a port. Then finally there are 2 buttons, program and reboot. The program button is not actually needed because this board is clever enough to go into program mode when the logic on the cable says so. Some boards you need to have to hit a button, this one you do not. If you hearken far enough back to the olden days, people knew that a program was contained in the entirety of void main void, even though that's not the right signature. Everything happened in one function. Life was simple. Life is that simple again. Almost. Now we have two functions. We have setup and we have loop. Setup is like your main. It's called one time. Loop is sort of a utility function that's called for you repeatedly. Loop is nothing you couldn't do with a for loop inside of setup, but I digress. So assuming you have the software requisites as described in the description below, then starting a project is as simple as file new project from within PlatformIO. When you click new project and the wizard completes, you'll wind up with a single source file, main.cpp, with two functions, setup and loop. Or here is that file. I'm going to build and program this, even though it does absolutely nothing, just to confirm that I can compile and communicate with the chip. I have no header files even included in this. This is pure C, so, well, it's C++, so it's not quite pure. All right, that is all we expected to happen. If we want to do anything meaningful, we're going to wind up using the Arduino SDK. And so, that is our one include that we're going to need as a minimum. But that will serve us well for quite some time, believe it or not. So if we look at our 4 goals of lighting an LED, blinking an LED, dimming an LED, and then color cycling an LED, to start, we need to be able to turn an LED on. So let's do that. How do you do that? Is it as simple as pin equals on? Well, it almost is. It's actually 2 steps. One, tell the microprocessor that you're going to use that pin for output, and then set the output to a particular value, 0 or 1, whichever you like. Now, before I start hard-coding pins 16, 17, and 18 in here, I'm going to use a modicum of style and air handling when I'm showing you code, because I don't want to show you egregiously bad habits, but I don't want to rat hole into some exception handling and interrupts and blah. So those 3 statements will allow us to push values out on those 3 pins. Why all 3 at this point if we're just doing red? Well, because they're clustered as a tricolor, I want to make sure the other 2 are in a known state, so we'll turn them off. To set the pin to a known value, you simply call digital write with the pin and the value. And since we want to turn the LED on, we'll set high. And we'll set the other 2 low. Alright, if all goes well, we'll wind up with a red LED. First we will see, of course, the flashing of the green LED, which is the program LED. So once that is over, so that looks cyan to me.
Inconceivable!
I grew up in a paint store, so I know my colors, and that's not red, that's cyan. Green and blue mixed together. Which tells me that it's probably everything except red. So I'm going to guess we got our logic states backwards, and that when we wanted to turn on red, we actually wanted to set it to low, and we wanted to set the off ones to high. I don't want to just invert and test again and hope it works, not knowing why, because we should have looked at the data sheet in the first place. Let's do that now. We'll go to EasySBC.com, the manufacturer, and we see there are 2 versions of the board. One has the antenna built into the main PCB. The other is the one we're using. It has the balun. So let's take a look at that. They otherwise seem identical. We go to downloads, and there's no downloads. Well, that's not good. So let's check the other one. All right, there is a schematic here, and they appear to be the same, so we'll just assume it's the same schematic. Okay, right away I can see 2 tricolor LED packages, one there and one here. This one is connected to pins 13, 14, and 19, so this must be the one that we see as the communications LED. This is the status LED that we are trying to play with. And indeed, pins 16, 17, and 18. But I see 3.3 volts coming in.
Yeah, what's your point?
That means to turn them on, we need to supply ground, which is 0, which is low, which is why it was backwards.
I see.
So by looking at the schematic, we can clearly see that we are expected to provide the ground side of the equation in order to activate the LED. Now that we know the cause of our problem, let's go back and fix it. We'll fix those values, re-upload. We'll watch the green lights go for the program mode. And when it's done, aha, finally, red, just as we always wanted. Okay, now that we've got a red LED, that's the first of our 4 steps. Now I just want to blink it. That should be pretty straightforward. We know we're already called in a loop, so we should be able to do something repeatedly here. First thing I'm going to do is move these 2 digital lights up to the top, because we only need to do them once. We're just going to set green and blue to off, which is high. And if you're wondering why I don't define off and on as the inverse, high and low, it's because it could be different for different LEDs, and high and low mean the same thing throughout a project, but on and off might have varying meanings, so I can't assign them to 0 or 1. It really depends on the circuit or the LED or the branch or whatever that you're dealing with. We're going to turn it on. We're going to delay for 1,000 milliseconds. Okay, so within our loop, we are going to turn the pin on. We're going to wait 1 second, turn it off, wait 1 second, and return, only to be called immediately again and do the same thing over and over again. So we will, for all intents and purposes, eternally flash this LED if things work correctly. Let's see if they do.
You know why this Mac compiles so slow, right? It's not enough subscribers. If I could just get more people to subscribe, this Mac would compile way faster.
There we go, cycling and 1 second updates. Actually, be every 2 seconds. 1 second on, 1 second off.
If you look closely at the LEDs when they're not lit, you can actually see all 3 color elements in there.
I'm going to speed this up by a factor of 10 and reprogram it. Re-upload it. And it's uploading away. And there we go. Much more rapid flashing. 5 times a second. Well, that accomplishes our turning on and our blinking. Dimming is a little different. You can't dim an LED directly by simply varying the amount of voltage or current to it. You can get away with obviously some brightening, but a sort of it's not the way you do it. The way you do it is to run the LED at its correct stated proper current and either have it on with that current or off with no current. Never in between, but simulating in between by being rapidly transitioned off and on, off and on, off and on, so that the human eye sees it as a steady state dimmed duty cycle. Now, if you remember back in the bad old late 90s, early 2000s perhaps, if you're that old, or if you've seen a Cadillac from that era go through your field of vision while your eye is scanning the other way, you might have seen sort of like a stack of visual images of the LED from the taillight. What that is the taillight cycling off on, off on, off on as it goes through your vision, but not doing it quite fast enough to be convincing, so you actually see individual on images. Cadillac eventually improved their LEDs, and the Escalade now has frankly a gorgeous light signature. I think it's probably the nicest light signature in vehicles, but it took them a while. So we're already quite a bit of the way there just by blinking it as we have here. What if we just blinked it really quickly? Let's give it a shot. We're going to turn it on for only 1 millisecond, and then turn it off for 9 milliseconds, and repeat. And that should, 100 times in a second, turn it off and on very briefly, giving us the image of a dimmed LED.
So we know we'll be called 100 times a second because we're only consuming 10 milliseconds total, and we're running in a tight loop, so 100 times a second.
Sure enough, a dimmed LED. It may not look that dim on video. These are not linear down when you get close to 0, but it is significantly dimmer than when it was on full duty. We're using a full core of a 240 megahertz processor to turn this LED off and on very rapidly and give it the effect of dimming. So it would sure be nice if the chip would do some of this work for us and not tie up the whole general purpose core. And indeed, it has 16 pulse width modulator generators for you. You just assign one to any particular pin, tell it what frequency and what resolution you'd like it to run at, and let it rip. Let's go through those steps because there's really only 3 functions you need to call. The first is LEDC attach pin. That attaches PWM generator number 1 to the red pin. Now we need to tell how fast to run. This doesn't provide a value to run at, just that when it does run on channel 1, run at 12,000 hertz with 8 bits of resolution. You'll have to refer to the docs in terms of what resolution works with what frequency. I know this combination works, but it does vary depending on frequency. And that's it. No libraries to call, no COM to invoke, no messages to pass. Just push some stuff on the stack, and load our new address. Old school. Anyway, enough reminiscing. Let's blink it still. But first, we'll turn it on. Then we'll turn it off. So this won't show any ramping or dimming, but it will show us two dim states. Dimmed all the way off and dimmed all the way on, and show us that we're able to command those two states individually using the PWM generator. Then we'll play with all the values in between.
Perhaps I should attempt to implant the subliminal message that every time I compile, you wish to subscribe, subscribe, subscribe. I wonder if that works. Alright, red flashing LED is what we hope for. Now we're doing this of course with pulse width modulation, which means we're pulsing it a lot, then pulsing it a little, and from there we want to move to pulsing it in between. That's the way we can dim.
If you're wondering why the number 256, it's because the PWM generator, we've given it the range of 0 through 255, 8 bits, for the on value, and 256 represents the off, so you have to go one past for the off value. Now that we know that we can assign a 0 to 255 value component to the leg of each LED color, we need to come up with some function that will sweep us through the red, green, and the blue, and I could spend half an hour on color theory, or I can just tell you, hey, there's 6 segments in the color wheel, and I found a function in Instructable.com that will take a 0 to 255 index and return RGB for a color wheel. Let's steal that, shall we? Now, there's a bit of ugliness here. It does use global values, and I had to strip out some unused code. But what's left here looks like it works. As I suspected, it runs through the color wheel, splits that into 6, figures out which section you're in, and then which segment offsets within it. We don't really need to be concerned too much with it. I verified that it does work. It's a black box. We're going to strip this out entirely. And we need to set up the PWM generators for the green and the blue. We no longer need to set them this way, because they'll be set by the PWM generator. Alright, that'll be enough to get our PWM generator started for each of the colors. Now I'm going to pass in a smaller brightness value here in the hope that it doesn't overdrive the camera as bad and makes it easier for you to see. If 32 winds up being too small, we'll revisit. It's a value out of 256, so that'd be like 1/8. Now to write our values, as before, generator 1 gets the R value, generator 2 now gets the green value, and generator 3 gets the blue value. There, that will run through all 256 colors of the color wheel, generating the RGB triad for that color, and assigning each color component to one of the PWM generators that's connected to the color leg of the LED that matches.
Easier done than said.
Well, let's build and run it. Assuming it builds, and assuming it runs. Well, it built, it's connecting, it's a programming. I see something going on. Let's go see what's happening. Now, it didn't work when we did 32 here. Why is that? Well, they were awfully very bright. So again, I'm guessing it was the old, we assumed we wanted it to be small when we wanted it to be big, because they're grounds and not power. What if we did 255 minus R? And 255 minus G and 255 minus B. And then did a smaller step. I have a feeling that what that's going to do is give us higher numbers, which will give us more suppression and hence lower color values. So we should get a dimmed down version.
You know, if I had more subscribers, I could probably justify a faster Mac to my wife, so throw me a bone and maybe subscribe to the channel so you don't have to sit through these slow compiles.
Sure enough. I'm going to speed up the color cycle by a bunch here so you can perhaps appreciate it better as well. Re-upload it and kill the light. Ooh, there goes your bright flash for the flash. There you go. There's a color cycle for sure. Well, there you have it. We made a $2 chip on a $7 board dance. Sort of. What I didn't tell you up front, this is the old school way of doing it. Nobody does it this way anymore. Actually, yeah, they still do. So you do need to know this method, because unless you have WS2812B LEDs, and they're not super prevalent yet, you do need to know how to control these. But shortly, in our next episode, we'll be moving on to WS2812B, which are digitally controlled. So rather than switching them off and on really fast, we just give them color codes like, hey, here's your 24-bit code. Go be a color. It's a lot simpler. But I wanted to make sure we knew how to do it the old way first. Well, happy color cycling, and I'll see you on the other side. Well, I hope you found today's episode some combination of interesting and informative. If you did, I encourage you to let me know by liking and subscribing. And most importantly, turn on the bell notification so you find out when the next episode comes out. Otherwise, this is such a small channel that you'll likely never stumble across it again. So pause and subscribe now if you would. If, on the other hand, you didn't find it interesting or informative, I suggest you watch it again on 75% speed, and then vote it up or down. Join me next time as we jump straight into the digital control of WS2812B LEDs and start building the Ring of Fire. Thanks, and good night.
Well, hello everybody. My name is Carl. C-A-R-L, Carl. I'm the cameraman. Good night, everybody. Don't forget to subscribe.